In this video, I'd like to talk about antiderivatives. Two of the big ideas from this course are derivatives and antiderivatives. We've obviously already learned our derivative rules, and so in this section, we introduce the antiderivative rules. Be sure that you memorize each of the formulas that we cover in this section. So to start this off, let's assume that the derivative of capital F of x is equal to lowercase f of x. If this is the case, then we call capital F of x the antiderivative of little f of x. So on here, let's look at an actual application to understand this notation. So what we're going to do is look at little f of x and assume that it's equal to 3x squared. And then they're going to ask us to find the derivative of that, which is going to be denoted capital F of x. So basically here, what you want to do is you want to think that I've taken the derivative of some function that's unknown, and I've received as my answer 3x squared. So in this particular situation, the thing that I've taken the derivative of would be the antiderivative of 3x squared. So thinking about rules for derivatives, on this particular problem, if the result is 3x squared, we can think of a possible function that I could take the derivative of to give me 3x squared would be x cubed. Because I know that if I use the power rule for derivatives, I would take the 3, that's the power, I would multiply it to the front, and then I would reduce the power by 1, making it 2. So I could take the derivative of x cubed, and that would give me 3x squared. So on here, I'm going to put a possible antiderivative function, use capital F of x, would equal x cubed. All right, now my question is here, is there more than one antiderivative? Well, think of this. If I come down and think of another function, such as this, we agree that taking the derivative of that function, x cubed plus 5, we would use the power rule on the x cubed part, and we would get 3x squared. And then taking the derivative of 5, we would end up getting 0. And so there, 3x squared plus 0 is 3x squared. So that would also be a possible antiderivative. Okay, so we're going to write another is capital F of x equals x cubed plus 5, since taking derivatives of constants yield zeros. So if we extend that particular idea, there's actually infinitely many antiderivatives for 3x squared. As long as we start with an x cubed, we could add or subtract any constant to that, and taking its derivative, we'd always get 3x squared back. So on here, what we're going to say is, for this particular question, we're going to say, in general, our antiderivative here can look like f of x equals x cubed plus or minus any constant that we desire. So as long as we use x cubed and then plus or minus a constant, then if we take the derivative of that function, then we'd get 3x squared back. So here, the antiderivative of 3x squared is x cubed plus or minus a constant. And you can get away with just plus the constant because the constant might be negative. All right, on here, we have a special kind of notation that we're going to see used in this section, and it's indicating perform the operation, find an antiderivative. So we see here in the notation that I have down below, there's this unusual looking notation here. Basically, that's indicating to us take an antiderivative. That actual symbol is what we call an indefinite integral symbol. So indefinite integral symbol. All right, and then here the f of x is what we call an integrand. That's the thing we're trying to integrate. Or it's the thing we're trying to find the antiderivative of. And then here at the end, we have this dx notation. That dx notation is going to become especially important later on when we talk about the chain rule for antiderivatives. But here, this is called the differential. All right. And then over on the right-hand side, we have the capital F of x notation, which we've just learned means antiderivative. All right. And then we have this plus c that we've talked about up above, and that is called the constant of integration. So on here, because we're introducing some new notation, it's important to understand what each of the symbols in the notation means. Overall, this particular concept, as far as the symbols are concerned, is called an indefinite integral. Later on, we're going to look at what we call a definite integral. So just kind of know that that's coming up. All right, so on here, the integral symbol means that we're going to find an antiderivative. Notice that our antiderivative is always capital F of x and then plus a constant. The constant's very important to remember. So as long as you're always taking a antiderivative, then you're always going to have a plus c at the end of your antiderivative function. So on here, we've got rules for integration. The first is the power rule for integration, and this is where I was saying earlier, make sure you memorize each of these rules. The power rule for integration says if you're trying to integrate x to the n power, then you're going to increase the power by 1, divide by n plus 1, the power plus 1, and then you're going to add c. But the only thing about this is not good for powers that are negative 1s. That being the case, if we assumed that our power could be negative 1, do you see that if you plugged n equals negative 1 in on the denominator, then you'd have negative 1 plus 1, which would end up being 0. You'd be dividing by 0 if you're using this rule. So it's important to remember here that the power rule for integration does not apply if n is equal to negative 1. So what I've done for each rule is I've done a very simple example of each so you can get an idea of how they work. So on this one, we want to find the indefinite integral of x to the 4th dx. Make sure that when you write integrals, as long as you have this integral symbol, then you should always look at whatever variable you have there, and you should always have d, that variable right next door as the differential. So on there, let's say your variable is y, then you're going to have a dy. If your variable is u, then you're going to have a du. So a couple of important things, as long as you have an integral symbol, there should always be d of some variable, and the variable is going to match whatever variable you have here. Okay, now, actually using the power rule on this particular problem, the power rule says take the power that's showing and add 1 to that. Whatever that power is, divide by the exact same power, and then add c. You're finding the antiderivative of the function x to the 4th. So in doing that, we're now going to reduce. So 4 plus 1 in the power is obviously 5. That same power will show up on the bottom, and then you'll have plus c. Now notice, I'm not going to do this except for on this first problem, but make a note that to check these type problems, if you were to take the derivative of the result, x to the 5th over 5 plus c, using power rules for derivatives, you would take the power of 5 and you would multiply it out to the front, and you would reduce your original power by 1. The over 5 we have is just a constant, so it stays there, and then the derivative of a constant is 0. And so reducing that, the 5s are going to cancel out, And then you're going to be left with x to the fourth, which is our integrand. That was the thing that we were trying to integrate originally. And so there we notice that taking the derivative of our result should always get us back to what it was that we were trying to integrate. Okay, so that's I'm going to say easy visual check as far as knowing if you have the correct answer or not. We don't do that very often except for just if it's easy, a quick glance. Sometimes it can tell us that our answer is wrong very easily if we've done something incorrectly. All right, the next rule is the constant rule. So basically here, we're saying that if we have a constant that's multiplied by a function, we can draw that constant out in the front of the integral and then just do the integral of the function. We have a similar rule for derivatives. We said that if we have a constant multiplied by a function, you can pull the constant out in front, not involve it in the derivative, and then just take the derivative of the function part, and when you're done, multiply it by the constant. It's the exact same idea here. So here we have the antiderivative, or the integral of 2x to the fourth dx. So the 2 that we see that's a constant here can be drawn out in the front, and then you can integrate x to the fourth dx. All right, when you're done, you're going to multiply whatever result you have by the 2. All right, on this particular problem, we've already integrated x to the fourth. We found out on the prior problem that that was equal to x to the fifth over 5 plus c. So we can say this should technically be 2 times x to the fifth over 5 plus c. And then if you distribute through, you're going to end up with 2 over 5 x to the fifth, and then plus 2 times c. However, when we do these particular kind of problems, we don't say 2 times c, we just say c. The constant we don't necessarily care about at this particular point, we just care that we're adding some type of constant number. So you're going to see 2/5 x to the fifth plus c as your actual answer. On this particular problem, what we're going to actually end up seeing as far as work is concerned is when you actually perform this particular problem, you're going to say it's 2 multiplied by x to the fifth over 5. And then we're going to keep the c separate out to the side. Okay, so we're going to see it 2 over 5 x to the fifth and then plus the c, and you're never going to do that distribution. And like I mentioned, the reason for that is you don't care what the constant is at this point, you just care that it is a constant. All right, the next one is sum and difference rules. Essentially here, what we're saying is that if you want to integrate the sum or a difference of a couple of functions, you can integrate each piece separately and then add or subtract them together when you're done. So in this particular example, it's asking me to find the antiderivative, or the integral, of x cubed plus x squared dx. And so we can break this up as 2 separate integrals. Now be careful with your notation. When you break them up, you need a differential with each integral. So remember we said earlier, as long as you see the integral symbol, then look at whatever variable you have here, and you're always going to need d, that variable, at the end of that. Okay, so we're going to say integral of x cubed dx, and then notice we have the plus sign here, we're going to carry to the middle, and then integral of x squared dx. All right, and then doing that, you can integrate both pieces separately. And so on here, if we integrate x cubed, then we add 1 to the power that's showing, and then we divide by that exact same power. Now technically what we would do is we would say plus c. I'm going to call it a c1 in this particular situation. And then plus over here, if I integrate x to the second, I would say it's going to be x to the second, or 2 plus 1, and then divide by 2 plus 1. And then technically we'd need another constant. Let's call it c2. All right, and then at the end of this, you're going to have an x to the fourth over 4. I'm going to skip over the c1 just for right now and go to this variable part. That would be an x cubed over 3. And then you would add your C1 and your C2 together and get some other constant. We don't care what the constant is. We just care that there's a constant showing. And on these, what you will actually see as far as work is concerned is on this particular step, when you actually work these problems, you're going to see it written x to the 3 plus 1 over 3 plus 1. They will skip that C1 constant. They'll go to the x to the 2 plus 1 over 2 plus 1, and then just add on a single constant at the end. And so when you're done, you're going to get the x to the 4th over 4. You're going to get the x to the 3rd over 3, and then just a constant c. Okay. All right. Next thing down, we do exponential integrals. I've got two rules here. The second rule works always for any exponential that's got a base of e. However, the first one is so common and so important that it really should be memorized second. I'm going to say separately. If you remember, when we did derivatives, if you take the derivative of e to the x, you get e to the x back. It would only make sense then that if you're trying to take the antiderivative of e to the x, you're going to get e to the x back. But remember here, you'll have plus a constant. So this very first one is important in that it's so simple. The next one is if you end up with, oh, and I have a mistake here in my notes we need to correct. This should say integral of e to the kx, and then please mark this out. That right there needs to say dx. So if we have integral of e to the kx dx, then taking that integral, we get e to the kx, which is the same exponential, but then you're going to divide it by the constant k, and that constant k was the value that was multiplied there in front of the x and the exponent, and then plus c. All right, so please do make sure that you correct my typo on this particular problem, and then make sure you know that formula. So let's apply this formula for the integral of e to the 4x. So notice here it's a base e function, and that's important. If we change to a different base, we have a different rule, but it's a base e function, and then we notice here that the value multiplied in front of the x in the exponent is 4. So using the rule exactly, we would have e to the 4x, so the exact exponential, divided by whatever the constant is here that's multiplied in front of the x, so 4, and then plus c. Now, a couple of things that I need you to know about that particular rule. That rule is only good if the power on x is 1. So if this function changes to e to the 4x squared, this rule no longer applies. So it's a very specific rule only for constant multiples of x as far as the power on your e. All right, now we mentioned earlier when we did the power rule that the power rule for integrals does not apply if your exponent is -1, because in doing that, you're going to end up dividing by 0. It turns out here that if you look at the integral of 1 over x dx, also consider that that integral could be written as integral of x to the -1 dx. So those two integrals are indeed the same integral, that it equals the natural log of the absolute value of x plus c. So this is also a problem that we're going to need to memorize. Now, this one should also make sense to you. So I'm going to come over here on the side and put a recall for you. Remember what happens when you take the derivative of the natural log function. The derivative of natural log function, because the base is e, it was 1 over natural log of e. It was 1 over the argument, which in this case is x, and then times the derivative of the argument. Natural log of e is just 1. We're multiplying by just a 1 there, just a 1 at the back, and so this derivative was 1 over x. So the derivative of natural log of x is 1 over x. So if you go backwards from there, you think of antiderivative as the opposite of derivative, then if you take the antiderivative of 1 over x, it would only make sense that your result is the natural log. Now, the important thing here is for algebraic purposes, since we can't take natural logs of negative numbers, you need to make sure that you put whatever value you have here, in this case it's x, in absolute values when you take the natural log. All right, so let's use this rule and maybe another on this particular integral. This one says they want you to find the integral of -2 over x dx. I don't, in this particular situation, change that x in the denominator to an x to the -1. I usually remember this particular rule just as it's written. If I have the integral of 1 over x, then I know it's a natural log. So I normally just leave that x down in the denominator. However, we have this -2 on the top. Remember, we have a constant rule that says if you have a constant, you can pull the constant out in the front and then multiply by the result of whatever the integral is. If I pull the -2 out in the front, then I'd have a 1 left in place in the numerator and then an x there. And do we see here, this now exactly fits the rule. So this would be -2, and then the integral of 1 over x dx is the natural log of the absolute value of x plus c. All right, and that would be as far as we're going to take that one. We can't actually multiply the -2 by the natural log of x since we have an x variable in there. All right, now here's what I'd like to do. I want to look at some examples and go through these and make sure that we understand that on some problems we have to do algebra before we're able to use a rule. We also need to understand that in order to use a rule, it must fit exactly one of the rules that we've looked at. Okay, and if it doesn't, you have to be able to rewrite it so that it fits. This very first example, I could actually call a rule, but I'm not for right now. What I'm going to do is explain it using the power rule. This particular problem is the integral of just a constant. Would you agree I could rewrite this as the integral of 2 z to the 0 dz? So in other words, recall that I'm going to say any value that's not 0 raised to the 0 is always equal to 1. All right, so on this particular problem, the constant 2 doesn't have a variable with it. Well, I don't know how to integrate a constant just by itself, but I do know how to integrate a power. And then at this particular point, there's the rule that says if you have a constant multiplied by some power, then you can pull that constant to the front and then just integrate the power. Notice here also our notation, we see we have z as the variable in the problem, and so to the side you have dz. Right, then using our power rule, it says take the current power, add 1 to that, and then divide by that exact same number. So our current power is z to the 0. If we added 1 to the power that we currently have, we're going to get new power of 1, and then plus c. So that's going to equal 2 times z to the first over 1 plus c, which is just 2z plus c. All right, so what I'm actually going to do on that one, I'm never going to show all those, I'm going to say all those steps for that particular problem, but I did want to show you at least where it came from. So I'm going to put here, new rule. If we're trying to integrate, let's say some constant dx, then we're always going to get c times x plus, and I'm going to use cap c there for my constant of integration there at the end. Okay? So it'll always be whatever constant you have times the variable that you're integrating with respect to, and then plus your constant of integration. All right, so coming down below, let me look at this problem. This is a combination of a bunch of problems that we've looked at so far. This one we have, it looks like a difference and a sum. We've got some powers. We've got some constants multiplied by x, and then we have just a constant at the back. So what we're going to do here is we know by sum and difference we can take the integral separately. I'm not actually going to write the steps of taking those integrals separately. I'm just going to do the integration. So here we know we multiply the constant. We don't have to involve that in the integration. With the x to the second, we increase the power by 1. That would become x to the third. And then whatever power you put there, you also divide in the bottom. Now notice there I skipped some steps that I have been writing. Write the steps as long as you need them, but if you get to the point of saying, okay, I know this is going to be x to the third because I'm increasing the power by 1, and then I'm dividing by the exact same number, you can leave those extra steps out. This one would be minus 6. Notice here that the understood power is 1. If I increase the power by 1, it would become 2, and then I divide by that exact same power. And then here, plus 3, and then I'm going to use the rule that we just developed in part A, and that is if you're taking the antiderivative or the integral of just a constant, it's going to be that constant multiplied by whatever variable we're integrating with respect to. So it'll be times x, and then finally at the end plus c. All right. This particular problem, it didn't really, I'm going to say, need too much more. If you have some reducing to do, we can go ahead and do that reducing. We see here that 2 and that 6 could reduce to 3. And then otherwise, we're just going to kind of rewrite. This one, we have the 5 on the top and the 3 on the bottom. That really should be written as 5/3. And then just write the x to the third to the side. This will be minus 3x squared. And then plus 3x. And then plus a c. And there is our antiderivative. On these particular problems, because they're simpler questions, it's very, very easy to visually look at that particular problem and take the derivative in your mind and make sure that the derivative is equivalent to what you have up here. But on harder problems that we're going to get to later on in this section, it's not really that easy. And so if you're, I'm going to say, confident that you're doing the right steps, you don't necessarily have to check to make sure that the derivative of the result is equal to the integrand, as we've done earlier. All right, next problem down, we have an issue. And the issue is here, this doesn't fit one of our rules exactly. As it's written, it's a root, and we don't have a rule for how to take the antiderivative of a root. However, we know from what we've done with derivatives that we can always rewrite a root as a fractional power. So we're going to rewrite the square root of z as z to the 1/2 power, and then dz here. All right, once we've rewritten it, now it fits our power rule exactly. All right, so on this one, the 5 is a constant, so we're not going to involve it. Now on this one, I am going to write the step the first time I do it, since we have a fractional power. This will be z to the 1/2 plus 1. But I'm going to be creative about the way I write that 1. I'm going to write my 1 as a 2/2. That way I already have a common denominator there with the 1/2. And same thing on the bottom, I'll do 1/2 plus 1, but I'll write the 1 as a 2/2. Okay, and then that should also then be plus c at the back. All right, and then reducing, we're going to have 5 multiplied. We have z to the 1/2 plus 2/2 power. That would be z to the 3/2. And then that will be over 3/2 plus c. And then on these, if you have a fraction that occurs in the denominator, what you do with that is you multiply by the flip of that. So we remember sometimes when we do division, we say keep it, change it, flip it. Well, we're dividing by a fraction. So we're going to change division here to multiplication, and then we're going to multiply by the reciprocal of the fraction we have on the bottom. So we're going to say 5 multiplied by 2/3 and then z to the 3/2. Be careful, make sure y'all keep the exponent of 3/2. That doesn't change. Okay, then what you can do, you can put the 5/1 and then either reduce it or multiply it. In this case, it doesn't reduce, but we can multiply. So 10/3 z to the 3/2 and then plus c. And for the z to the 3/2, you can leave that as a fractional exponent. You don't have to change it back to a root unless you really want to. We wouldn't want to leave any kind of negative powers. Okay, we're good on this one though. All right, the next one down is similar in that right now, the way it's written, it doesn't fit a rule. But we know that if we have x's in the denominator, then we can write them as x's in the numerator if we change our exponents to negatives. Now, do be careful. This is not the same thing, obviously, as 4 over x dx. If it was 4 over x dx, that's going to integrate to a natural log because it's just a single power of x in the bottom. But this one, we have not just a single power, but an x to the third. So we're going to rewrite this using negative exponents. We're going to do 4x to the negative 3, and then dx. All right, the 4 is just a constant, so it's just going to stay. And then here, I am going to write this the first time I do it. We're needing to increase this power by 1, so it'll be negative 3 plus 1, and then divide by that exact same number, and then plus c. I can't emphasize enough how important this plus c is. Make sure, as long as you have this symbol, then you're going to have a plus c in your answer. The other thing is when you actually use a rule that changes the problem from looking like an integral to looking like a function, that's the point at which you put the plus c. So basically, when this symbol disappears, then you're going to have this symbol on the next step. All right. So on here, we're going to have 4 multiplied by, this would be x to the negative 2, divide by negative 2, and then plus c. And then as we had in derivatives, we don't want to leave negative exponents in our answers. Okay, however, on this one, be a little bit careful. We want to reduce this 4 is over 1. We can reduce the 4 and the negative 2. That's going to leave us a negative 2 in the top. So we're going to have negative 2. And then we have this x to the negative 2 still. And on there, what we can do is we can write the negative 2 as negative 2 over 1. And then basically just slide the x to the negative 2 downstairs with that understood 1. So it'd be negative 2 stays on top. The x to the second drops to the bottom, and then plus the c. We don't need to write the 1 that was in the bottom to hold place. All right, now what we're going to do is look at some more difficult problems. That particular page was mostly simple questions with a little bit of rewriting to do as far as making the form fit. This particular problem, there's multiple issues with it. The first thing I need y'all to know is that for integration, there is no product rule, and there is also no quotient rule. We're going to be able to integrate products and quotients, but not by using a particular set rule for each particular kind of problem. So I need y'all to know you cannot integrate a product using a rule. So right now, if you have something that's a product, you better be able to change it so that it's not a product. So at this particular step, the very first thing I'm going to do is change that root of x, square root of x, to x to the 1/2. So keep the x that was in the front, change the square root of x to x to the 1/2. Then I need you to remember some rules of exponents. This would be an understood 1 for that exponent on the single x. However, I'm going to write it as 2 over 2 since I have a 1/2 power on my other x. Some rules of exponents say if you have the same base and you're multiplying, you're going to add your exponents. So I can change this from something that looks like a product to something that's just a single x. So this would become x to the 3/2 if I add those two powers together. Now it's important, what I just did was just purely algebra. This was not calculus of any kind. It was not using an antiderivative rule or derivative rule. That was just algebra. Then from this particular point, you're taking the antiderivative of a singular x to a power. We've got a rule for that. So on this one, we'll say this will become x to the 3/2 plus 1. We're going to write the 1 as a 2 over 2. And then we're going to copy that down to the bottom. And then plus c. And then going from here, x to the 3/2 plus 2/2 is x to the 5/2. And then that would be over 5/2 on the bottom. And then remember we said if we have something that's divided in the bottom that's a fraction, we're going to flip and multiply. So it's actually going to become 2/5 multiplied by x to the 5/2 and then plus c. Okay, so make sure here that y'all put there's no multiplication rule. So if you see an integrand that's being multiplied, then right now you know you should be able to change it to something that's not being multiplied so that you can use, let's say, a power rule on it or something along those lines. All right, the next question down is a favorite question of mine because it involves a couple of different functions, and it means that you're having to pay attention to multiple rules at the same time, and this can happen to you quite frequently. So on here, the very first thing I'm going to notice is that this is a constant over a single power of x. So I know that this one is going to integrate to a natural log of absolute value of x. Okay, that's the rule I'm going to be using. The 5 is going to be a constant on that. On this one, I'm going to say it's going to integrate to a e to the kx over k type of problem. So I'm needing to think about two different rules within this one problem. All right, so for the first one, the 5 is just a constant, so I'm going to leave the 5, and then the over x is going to integrate to natural log of absolute value of x. And then for the next piece, the negative 3 is just a constant, and then we have the e to the constant power of x, e to the negative 2x. So it's going to be e to the negative 2x, so basically the exponential itself, but then you're going to divide that piece by the constant that's in front of x. So divide it by negative 2, and then we're going to put plus c. All right, so simplifying this just a little bit, really the only thing we can do, we see here we have a negative here and a negative there. Those are going to be able to be reduced. Here we can't really do anything with the 5 natural log absolute value of x. I am going to write this as a 3/2. And then we have the e to the negative 2x plus c. Now on the exponential functions, when you see e to the negative 2x, if you see e to the negative 2 and there's no x, then quite obviously the exponent is negative. However, when we see e to the negative 2x, because we don't know what the variable x is, we don't honestly know if this exponent is negative or not. If the x value happened to be negative, then you'd have a negative times a negative being a positive in the exponent. So conventionally, usually we don't rewrite an e to the negative constant power of x by writing it in the denominator, making the exponent positive. You could, but you don't have to. Okay, so I'm going to put on here an alternate answer if you want to, but also tell you you absolutely do not have to do this because you don't know what x is. So we could also write this as 5 plus natural log absolute value of x, and then 3 over 2 e to the 2x, and then plus c. But conventionally, we normally just leave it right here. All right, next one down. This one's also awkward in that we don't have a quotient rule. So we need to put ourselves a note. There is no quotient rule. And it's not like I'm saying that right now we don't have one. I mean, there's not one. There's no product rule for antiderivatives. There's no quotient rule for antiderivatives. Okay, does that mean we can't do this? No, it just means we can't do it so long as it looks like a quotient. So on here, what we're going to do is if you have just a single term in the bottom, you can actually split this. So we're going to take it, we're going to say it's the integral of, and then I'm going to use parentheses here because we're going to have multiple pieces now. The first term here, you have over x squared. So that'd be an x squared divide by the x squared you have on the bottom. And then keep the sign that's next, it's plus, and then take the next term in the top, 2x over x squared. And then take the next sign you have, that's plus 1 over x squared, and then dx. Well, we still have quotients, but let's look and see what happens when we reduce. When we reduce x squared over x squared, that's just 1. I can take the antiderivative of 1. The next thing over is if we look at the 2x on the top and the x squared we have on the bottom, we could cancel a single x from here and a single x from there. And so that's going to leave us with a 2 on the top and a single x on the bottom. I can take the antiderivative of that. That's going to be a natural log function. And then looking over on the last one, I can't take the antiderivative of 1 over x squared, but I can take the antiderivative of x to the negative 2. Right? So in this way, I'm able to take something that's a quotient that I don't have a rule for, split it up, simplify it, and then now I have a rule for each one of these pieces. So remember the rule for a constant only. So if you don't have a variable next to that constant, it's always that constant times the variable. And then this one, it would be 2. And then because it's understood 1 over x is what you're taking the antiderivative of, it'd be natural log absolute value of x. And then on this one, you're saying this would be power rule. So it'd be x to the negative 2 plus 1 divided by negative 2 plus 1. And then remember your good old friend plus c at the end. All right, so simplifying this one, you'll have just x plus 2 natural log absolute value of x. And then right here, this is going to end up being plus, this is x to the negative 1 over negative 1 plus c. And then the only thing I really need to do here is get rid of the negative power that I have on the x. So notice there what I was saying earlier, this is indeed a negative power because it's negative 1. Before, when we were looking up here at the exponential, it was negative 2x. We had a variable next to it. So this being a true negative exponent, we want to make sure to change it to positive exponent. All right, notice here we're dividing by negative 1. That's going to make everything there negative. And then the x to the negative 1 is going to fall to the bottom. This is going to become 1 over x. And then plus the c. All right. All right. Next one down, we have a similar, I'm going to say, situation as we had earlier, as far as this is a product, not anything that we know how to take an antiderivative of. But it's also a product that can be operated on. So on this one, notice that you could distribute through the 7x. And so on this one, we can rewrite this as integral of 7x cubed plus, and then multiply the 7x by the 9, so 63x. We're going to put that in parentheses. The integrand always needs to be in parentheses if there's multiple pieces to it, and then that'll be dx. And then we can just integrate each piece. So the 7 remain a constant. The x, we know we're going to be using power rule on that. We're going to increase the power by 1 and divide by that same number. Normally what we start doing at this point is just dividing the constant we have out in the front, if there is one. Same thing on the next piece. We have the 63 that would remain. The understood power here is 1. So if we increase that by 1, it gets to be 2. And then we're just going to take the constant we have out in the front, divide by 2. And then we have plus c. All right, next one down. The important thing here to remember is that x plus 3 all squared means write x plus 3 twice. And then if we write x plus 3 twice, we understand we need to FOIL that. So it will become an x squared plus a 3x plus another 3x and then plus 9. So that would become x squared plus 6x plus 9. So once again, we had something that in this case is not a single power on x. So we should point that out. This is a group of stuff raised to a power, but we don't have a rule for that. We only have a rule for x to the n. We don't have a rule for x plus 3 to the n. So we can't use a power rule on it originally. Well, if we think of x plus 3 all squared as being x plus 3 times x plus 3, we also don't have a rule for a product. But then when we multiply it out, we have a rule that would say how to take the antiderivative of each individual piece of the result. So that's what we'll do here, is rewrite this as antiderivative x squared plus 6x plus 9 dx. Okay, so integral of x squared would become x cubed over 3. Integral of 6x would be 6x squared over 2. Integral of 9 would be 9x, and then your plus c. And then we can reduce. The x cubed over 3 is just going to stay. This is going to reduce to a 3, so that's 3x squared, and then the 9x, and then the c. Okay, on this particular problem, we mentioned earlier that you can always check antiderivatives by taking the derivative of the result. But on this particular problem, if you took the derivative of your result, then you're going to end up seeing that you're going to get back to here, not necessarily back to what you had originally in there, unless you back up and you factor. All right, now, what I'd like to do to end this lesson is look at some problems where they're giving you information about a derivative, and then they're asking you to find an original function. If that's the case, then that's always going to indicate to you that you're going to take some type of antiderivative. So if you're given information about a derivative and then being asked to back up to the original function, that's going to indicate that you want to take an integral or that you want to find an antiderivative. All right, so on here, think of it this way. If you were to integrate a derivative, derivatives and antiderivatives or integrals are essentially opposite operations. So what you should get is you should get a function, I'm going to say plus or minus a c value. Now, this other piece of information is the piece of information that's going to allow you to find c. So allows to find that constant of integration. Okay, so let me show you what I'm talking about here. So I'm going to go ahead and use this notation. F of x is going to equal to the antiderivative of f prime of dx. We know what f prime of dx is. It is 5 minus 6x dx. And what I'm going to do is go ahead and follow down with the f of x notation. So f of x is going to equal, go ahead and take that integral. This will be 5x minus 6x squared over 2 plus c. All right. Now, the f of 2 equals 3 says that if I evaluate this function specifically at 2, I should get 3 out. So we're saying here, I'm going to change colors so you can see what I'm doing. If I evaluate this function now at 2, so that means I'm going to plug in 2. And I guess right here I should really reduce that to a 3. So 6 divided by 2 is 3. And then sub in this value 2. And I don't know what c is, but eventually this whole thing right here should equal to how much? Should equal to 3. So we see that is going to give me an equation that I can use to solve for c. So 5 times 2 is 10. I'm going to drop the f of 2 notation at this point. I don't need it. And then minus 2 squared is 4, and then 3 times 2 is 12. Plus c is equal to 3. 10 minus 12 is negative 2. Negative 2 plus c is 3. If I add over the 2, c would then equal 5. So right here, I had a function. Let me go ahead and simplify it. Little f of x was equal to 5x, and then I reduced the 6 over 2 to give me 3. So minus 3x squared plus c. But I now know what the value of c is. The value of c is 5. So they have asked me, given the derivative, find the original function. The original function was 5x minus 3x squared plus 5, and the original function evaluated specifically at 2 is equal to 3. So I've found the function that satisfies all those criteria in that situation. All right, let's come down here and look at it in terms, I'm going to say, of kind of a more applied approach. So this particular problem, it says find the cost function for each marginal cost function, do you remember there that marginal cost means you had found a derivative? So we notice on this first problem, they've given us marginal cost, and they want us to find the cost function. So on this, if you're on an exam, notice they've given you a derivative, and they're asking you to find the original. So the original function here would be c of x. So we're going to say that c of x is going to equal the antiderivative, or the integral, of whatever function they've given me. All right. So on this one, I'll say c of x is going to equal, integrating there, this will be 2x cubed over 3, and then plus 5x squared over 2. All right, on this particular problem, perhaps it would be a bad idea to use plus capital C as our constant of integration, because we're already using a c for the c of x function. So what you can do there instead is you can use, if you want to, a k. You can use a capital K, a lowercase k, just something different than c. All right, now, what does this mean? It said originally we have a fixed cost of $10. What that means, fixed would mean what it was originally. So at 0 items, we know that we have a fixed cost of 10, or a cost of 10. So that's giving me an ordered pair. That's going to allow me to find my k value in this case. So c of 0, 2 times 0 cubed over 3, plus 5 times 0 squared over 2, plus k should give me 10. Okay, leave off the c of 0 notation. You don't need that. Notice there that that's 0 and that's 0. So in this case, k equals 10. And so what you'll do is you'll say from this step, c of x then is equal, and we're probably going to write it as 2/3 and then x to the third to the side, plus 5/2 x to the second to the side, and then what's the value of k? We found out the value of k was equal to 10. And so there's our cost function that satisfies the criteria that they gave us. It has a derivative that is 2x squared plus 5x. Its fixed cost, or its evaluation at 0, is equal to 10. All right, so for our last question, let's look at something a little more complicated. This one, they said that the marginal cost function is x to the 1/2. It says when 16 units cost $45. The 16 units costing $45 means that c at 16 is 45. All right, so we're going to say to find the cost function, we're going to integrate the derivative function. Notice here we're having to make sure that we put the integral symbol saying we're going to take the antiderivative or the integral. We're having to put the dx notation there behind the x to the 1/2. Right? To actually integrate here, I need to add 1 to the exponent. If I think of 1 as 2/2, if I add 2/2 to 1/2, that's going to give me 3/2. And then divide by 3/2. And once again, I'm going to use k here instead of c. I'm going to go ahead and bring down the c of x notation. Because I have a fraction in the denominator, I'm going to flip that fraction and multiply. So this is actually going to become 2/3 x to the 3/2 plus k. And then I'm going to use the c of 16 equals to 45 to solve to find the k value. So c of 16 is going to equal 2/3 16 to the 3/2 power plus k. And I know eventually that value is 45. I'm going to drop the c of 16 notation. I don't need that. And then right here where we have the 2/3 and then 16 to the 3/2 power, instead of using a 3/2 power there, we're going to use root notation. So that's actually going to be the square root of 16. And then we can either raise 16 to the third underneath the root, or we can say that this entire thing is raised to the third. That would be easier in this situation. If we raise 16 to the third, we're going to get a large number. But if we take the root of 16 first and then raise that to the third, that's going to be easier to deal with. All right, we still don't know k, but we know this is 45. So this will be 2/3. The square root of 16 is 4. All right, and then go ahead and do 4 to the third. 4 to the third is 64. So we have 2/3 times 64 plus k equals 45. I'm going to put the 64 over 1, and then I'm going to go ahead and multiply that. So we're going to have 2 times 64 is 128, and then 3 times 1 on the bottom will be 3, and then plus k equals 45. We then would need to subtract over the 128 over 3, so k would equal 45 minus 128 over 3. And then there, if we found a common denominator would be 3. So I'd need to multiply the top and the bottom of that by 3 to get those fractions together eventually. So here k is going to equal to 135 over 3 minus 128 over 3. And then doing that calculation, k is going to equal, on that one, 7 over 3. All right, and then what you do is you go back and you look to see where it was that you had taken the antiderivative and then plugged in k on the second step. Here we were finding k. This is the step you want to look at and take and substitute your known k value back into. So at this point, you're going to say, so c of x is going to equal 2/3 x to the 3/2, and then plus 7/2 there for the final answer. All right, y'all let me know if you have any kind of questions.